In this lesson, we're going to cover Unit 7, Acquisition 3 on Solution Stoichiometry. So the nice thing about this is we're not really doing anything new. You know how to do stoichiometry from Unit 6. We talked about how to do a few conversions back in Acquisition 2. So this is just kind of putting everything together. So a few reminders before we get to the example problems. In many of these problems, you're going to have two givens. Always start with either volume or mass. Never start with molarity. Always start with either volume or mass depending on what the problem gives you. Remember that we can use molarity as a conversion factor. And what I mean by that is, let's say I have like a 1.7 molar solution. Molar just tells you how many moles of solute per 1 liter of solution. So 1.7 molar solution is just saying that I have 1.7 moles of solute per every 1 liter of solution. This is something we can plug in as a conversion factor. When do you use which conversion factor? So let's say the problem gave you grams. Anytime we're converting from grams to moles or moles to grams, the conversion factor that we use is the molar mass that we can calculate from the periodic table. Let's say you were given volume and we're converting from liters to moles or moles to liters. Moles to liters, we're going to use that molarity. Let's say we're converting between two different substances. I give you a quantity of reactant and I want to know how many grams of product could be made. So if you are converting from one substance to another substance, we're going to use the mole ratio. So those are just a few reminders. Like I said, this is all stuff that we've done before. We're just going to put it together into one big problem. First example. How many liters of 2.5 molar sodium hydroxide is needed to produce 10.0 grams of copper 2 hydroxide? How many liters of 2.5 molar sodium hydroxide is needed to produce 10 grams of copper 2 hydroxide? We also need a balanced equation. All right, so our first little tip or trick. Always start with either volume or mass, never molarity. So notice that I have two givens. I have 2.5 molar sodium hydroxide, 10 grams copper 2 hydroxide. We always say start with a given. Well, in this case, we have two givens. So that's why we need to remember this point. Always start with either volume or mass, never molarity. In this case, I have a mass. So that's what I'm going to start with. Remember, you should always be writing three things. First, the quantity, 10.0. Next, the unit, grams. And third, the substance. Looking at our conversion factors, I'm starting with grams. The only thing I can do if I have grams is to plug in molar mass to get to moles. I know I need my units to cancel, so grams go in the denominator. The molar mass was given to us in the problem. There are 97.57 grams in every 1 mole of copper 2 hydroxide. Grams divided by grams cancel. So now I'm at moles of copper 2 hydroxide, but I'm solving for sodium hydroxide. I'm converting between two different substances. So if I'm going from one substance to another, I need a mole ratio. We need both the unit and the substance to cancel out. So moles of copper 2 hydroxide will go in the denominator. And then we look at our balanced equation to figure out the number of moles. The number of moles will be equal to the coefficient, which is 1. Whatever you're solving for always goes in the numerator. So I'm solving for sodium hydroxide, and I have 2 moles of sodium hydroxide. Alright, so now I'm at moles of sodium hydroxide. I want to get to liters of sodium hydroxide. Going from moles to liters, I'm going to plug in the molarity. 2.5 molar solution means I have 2.5 moles per every 1 liter of solution. So think about how we're going to set up our conversion factor. I want moles to cancel, so that means mole would have to go in the denominator. And I have 2.5 moles per every 1 liter. So now moles of sodium hydroxide will cancel, and I'm going to be left with liters of sodium hydroxide, which is what I'm solving for. So now let's plug this in our calculator and see what we come up with. Multiply everything across the top, 10 times 1 times 2 times 1, divided by everything on the bottom, 97.57 times 1 times 2.5. Make sure you're using parentheses if you are doing the calculation all at once. And I got 0.08199, etc. Let's talk about significant figures. When we're doing multiplication or division, the rule is that we round our answer to the least number of significant figures. 2.5 has 2 significant figures. 10.0 has 3 significant figures. The least number of sig figs is 2.5 with 2 significant figures. So therefore, my answer can only have 2 significant figures. Leading zeros are not significant. So we're going to round this to 0.082 liters. Let's try another one. liters of 2.0 molar Ki is needed to produce 1.5 grams lead 2 iodide. So this problem is going to be very similar to the last one that we did, and that we're starting with mass and you are solving for a volume. So this would be a good problem to pause the video and try it on your own. Use the previous problem as your roadmap and see if you can solve this one. So if you want to try it out on your own, pause your video, solve, come back and see how you did. If you need the extra support, stay with me. So looking at the problem again, we have two givens. I have 2.0 molar potassium iodide and 1.5 grams of lead 2 iodide. Remember, when we have two givens, always start with either mass or volume depending on what you're given. In this case, I have a mass, so that's what I'm going to start with. If we're starting with grams, the only thing we can do is plug in molar mass to get to moles. Since grams are in the numerator, I know I need grams in the denominator because I need that unit to cancel out. I have 461 grams in every 1 mole of lead 2 iodide. Next, my given is PbI2, but I'm solving for Ki. I'm switching substances, so I need a mole ratio. So in the denominator, I have 1 mole of PbI2. We figure out the number of moles based on the coefficient from the balanced reaction. Whatever you're solving for goes in the numerator, based on my balanced reaction, 2 mole Ki. Alright, I need to get to volume of Ki. So if I'm converting from moles to liters, I can plug in my molarity. A 2 molar solution means I have 2 moles of solute in every 1 liter of solution. Again, we want our units to cancel. So moles of potassium iodide is in the numerator. I'm going to put moles of potassium iodide in the denominator. Lastly, if you were to stop and solve, your answer would be in liters. I want my answer to be in milliliters. So I can add one more conversion factor. For every 1 liter, there would be 1,000 milliliters. Let's plug this in and see what we come up with. .2537. Alright, we want to round to the appropriate number of significant figures. 2.0 has 2 significant figures. 1.5 has 2 significant figures, so my answer can have 2 significant figures. And then I want to add units, which would be milliliters. Another thing that I want to bring up is you can simplify. So 2 divided by 2 is going to be 1. You can simplify this. So now your math just becomes 1.5 times 1,000 divided by 461. Saves you a few buttons to push on the calculator. Alright, let's do one more, but let's go the opposite way. So for both of these examples that we've done so far, we started with mass and we solved for volume. So let's flip it. I'm going to give you a value and you're going to solve for the mass. How many grams of barium chloride with a molar mass of 208.23 grams per mole can be produced from 0.75 liters of 3 molar hydrochloric acid. For balanced reaction, we have barium hydroxide reacting with 2 moles of hydrochloric acid to produce solid barium chloride and 2 moles of water. So one thing that we haven't talked about with these problems are limiting reactants. So let's just assume that I have enough barium hydroxide for this reaction to occur. So again, I have 2 givens. I have 0.75 liters of 3 molar hydrochloric acid. Always start with volume or mass, never molarity. So I'm going to start with 0.75 liters of HCl. If I'm starting with liters, the only thing I can do is plug in my molarity to get to moles. A 3 molar solution means I have 3 moles of solute in every 1 liter of solution. 3.0 moles of HCl in every 1 liter of HCl. Again, always setting up our units so they cancel. So since I'm starting with liters, liters go in the denominator. Liters divided by liters will cancel out. Now I'm at moles of HCl, but I'm solving for grams of barium chloride. I'm switching between substances. If I need to convert from hydrochloric acid to barium chloride, I have 2 different substances I need a mole ratio. Both the unit and the substance have to cancel. Moles of HCl will go in the denominator, 2 of them. Whatever you're solving for will go in the numerator, 1 mole barium chloride. Lastly, I need grams. The only way I can go from moles to grams is by plugging in my molar mass. Again, we want our units to cancel, so moles will go in the denominator. Per every 1 mole of barium chloride, I have 208.23 grams. Moles divided by moles cancel, and we would be left with grams. Let's plug this in and see what we get. Alright, I got 234.25, a whole bunch of digits we don't need because we're going to round anyways. 0.75 has 2 significant figures. 3.0 has 2 significant figures. My answer can only have 2 significant figures, so I would round to 230 grams.